Oh, Dr. Prabha is also here. So you have all the three speakers, Archon?
Yeah, I think so.
Okay. I think it's almost time. Shall we wait
Yeah, I
for a
think.
couple of minutes or?
Yeah, we can probably wait for 1 minute. Just
Okay.
and then start. Okay, let's. So I'm sharing the screen and PPT.
Okay. Think, before that, thanks to all our speakers for accepting our invitation for the webinar. This is first of a kind we are doing from this platform, most on physics based. So this is a new experience for us even.
Yeah. So yeah, so now I guess we can start, Sean.
Yeah, I think it's better. It's almost 10:04, so yeah.
Yeah.
4 minutes past, so.
Yeah. So first of all, hi everyone. Welcome to SciROI Global's third focused webinar on emerging trends in quantum information sciences in India. We welcome all our participants for attending this webinar and wholeheartedly thank all our speakers and panelists for accepting our invitation to join us today. I am Archon, a postdoctoral researcher working at the Applied Physics Department of Yale University and an active volunteer for SciROI Global leadership team. Today, we will learn from the leading experts of premium institutions about this topic and gain insights about emerging trends in quantum information sciences in India. Today's webinar focuses on career opportunities in India and engage in meaningful discussion with panelists in the follow-up question answer session. I'm also accompanied by another SciROI volunteer, Shayan. So Shayan, can you introduce yourself?
Yeah, thank you, Archon, for the introduction. Hello, everyone. I'm Sayan. I'm a PhD student at Purdue University, working in geophysics. So, and also I'm again a SciROI volunteer. So SciROI is a volunteer-driven nonprofit organization that was founded by Professor Asim Ansari and Winstay Forward in 2015, with the mission to create awareness and aid in the smooth transition of the Indian STEM diaspora back to India. Over the last few years, SciROI has provided a platform for promoting multi-level collaborative initiatives between individuals and agencies in India and abroad, in facilitating the pursuit of a STEM career in India through our annual events, recruitment drives, focused webinars, blogs, and newsletters, highlighting the diversity of prospects in India. To learn more about our past activities, now Archon will play a short video.
Yeah.
Did you share the sound, Archon? I can't hear anything.
Oh.
Okay, you can reshare, yeah.
Yeah, we have to reshare this, I guess.
So this was a short video about all our activities that we have done over the past few years. We also have our upcoming annual event in the USA and in Germany in September 2024. Can you please go to the next slide, Archon? Yeah. So these are the list of our speakers from eminent Indian institutes. And this year, we are also focusing more on people with engineering and physics background. And as our webinar is also focused on that background, we want to take this opportunity to introduce our annual events to all our speakers and our participants. So we encourage people with similar backgrounds and also different other backgrounds to attend our event, either in USA or in Germany. So before we move further to our today's talk, I request all the participants to maintain the following etiquettes for the webinar, uh, except the speakers, of course. Please keep yourself muted throughout the webinar. Uh, please post your questions with your introduction in the Zoom chat. We'll try to accommodate as many questions as possible in the Q&A session after the talk. And if we have more time, we can have also chance to one-to-one interaction. Then we'll ask you to unmute yourself and ask your questions and interact with our speakers. And also, please keep your video on if possible for better interaction. Now, over to you, Archon.
Yeah, sure. So first, we will introduce our speakers for today. So first, we have Professor Prabha Mandayam from IIT Madras. She is an associate professor, Department of Physics of Indian Institute of Technology, Madras. Her research interests include quantum information theory, quantum error corrections, and many other domains of theoretical quantum computation. Then we have Professor Vanu Dash. He is a professor and director of Center for Quantum Engineering Research and Education, TCG CREST. So he is basically leading that effort of building a new center totally focusing on quantum computing related research at City of Calcutta. His research specialization is quantum many-body theory of atoms and molecules and its application to fundamental physics and quantum computing. Finally, we have Dr. L. Venkata Subramaniam. He is leading this IBM Quantum India effort on this domain. And also recently, he has published a book on this quantum computing effort of India. So now, so we will start today's webinar. At first, I would like to invite Professor Mandam to share her thoughts on our topic. So I will stop sharing my screen now. So please, Professor Mandam.
Thank you, Arshan. Am I audible?
Yeah.
Okay, well, thank you for inviting me to this. As I had mentioned to you over email, I think this is a very nice initiative. I was myself in a boat, as many of you, not so long ago, where I was outside India and I was looking to come back to India. Of course, you must remember that these were the pre-quantum hype days, which means this was maybe, before 2016, before 2014. So it was still an interesting task to come back and sort of navigate the waters here. And of course, there were tons of questions. These were the early days of the Inspire Fellowship. It had just come out, early days of the Ramanujan Fellowship. So there was a lot of learning that my generation of people went through. So I'm happy to take questions on that sometime during the Q&A and so on. But for now, I just thought I will give an overview. So I'm currently at IIT Madras. I'm looking to share screen. Just give me a second. Yeah, I thought I had a short presentation. So, yeah, sorry. Okay, so I guess you can see my slides. Yeah, okay. So I just thought I will tell everyone here a little bit about our center at IIT Madras, the kind of research that we do, and also a little bit about my own primary research focus, which is quantum error correction. Yeah, so first of all, I want to start with this advertisement that IIT Madras is hosting QCMC 2024. That's, if some of you know, one of the premier conferences, legacy conferences in quantum computing and quantum information. This is happening in IIT Madras between 26th to 30th August. Registrations are still open. We have a fantastic lineup of invited speakers, contributor talks, posters, and all of that. So those of you who would like to visit and attend, you're please welcome to register and attend. The Center for Quantum Information, Communication and Computing is about 3 years old now in IIT Madras. So I think we officially started as a center sometime in 2021. As you can see here, so we have a wide array of, we bring together a wide array of faculty in the center. So of course, the bulk of us are from physics and electrical engineering. So there's a lot of us here in physics. So this is, I don't know if you can see my pointer here. Can you?
Yeah.
Okay. So this is Professor Arul Lakshminarayan. He is one of the senior guys in this team here. So coincidentally, he was my master's thesis mentor, the one who got me into quantum information theory. So a lot of you may know him from quantum many-body theory, quantum chaos, quantum information. There's my colleague Vaibhav, who works on quantum metrology. There's Sunetra, who does quantum optics and nuclear physics. There's Professor Rajesh, who does many-body physics. Many of you may know Professor Balakrishnan. Yes. His lecture videos are all very popular. He's part of our center as well. There's Professor Lakshmi Bala, quantum optics. Then we have folks from electrical engineering, chemistry. So this is Professor Pradeep in electrical engineering, who works on quantum error correction codes. There's Professor Chaitanya from chemistry, Sanjeev from biotechnology. There's Professor Anil in electrical engineering, who works on implementing quantum communication protocols. I'll talk a little bit about that. We have some new faculty here, Siddharth, who joined us not so long ago. He works on NV center-based realizations of qubits and their properties. There are faculty in electrical engineering who also do fiber optics-based quantum systems, quantum queues, and so on. So the aim of the center was to really make this interdisciplinary and bring together people of various interests who can contribute in many ways to the domain of quantum science and technologies. Oops. Okay. So what does the center do? Yeah, we do a lot of research is, of course, the mainstay, advise PhD students and so on. The research, of course, you can think of it as basic, which is more the maybe on the theory front. And then there is the applied research where we implement QKD, where we work with, let's say, the IBM quantum hardware to try and run applications, algorithms, simulations, and so on. One major component of the center has also been the focus on education. So IIT Madras is one of the nodal agencies for something called NPTEL, which many of you in this audience may be aware of. We have successfully run several courses on quantum algorithms jointly with IBM. Venkat is, of course, here, so he may also talk a little bit about that. And we have also now started an executive education program on quantum computing. We have what's called a web-enabled MTech program and so on. In terms of courses itself, we now offer an interdisciplinary dual degree program on quantum science and technology. So this is to sort of tell you that, okay, so where does the funding for the center come from, right? So I showed you some of the partners here, the support that we get. Emphasis is an industry partner. So one component of the funding comes from industry as a sort of corporate social responsibility angle. But then there are also industries which are interested today in quantum science and technologies because of the sort of applications that they have, because of the promise of this technology. So there's Nagaro, there's LTI Mindtree. Then there are the national companies like BEL, which are collaborating with us on actually implementing QKD, implementing quantum networks. And then, of course, we have the premier government agencies, whether it's MATI or MHRD or DST, and their schemes and projects. Coupled with all this, there's also this education aspect, which today is also enabling us to fund various things in many ways. Okay. We have also enabled startups, Q Krishi, Q New Labs, Confluence. We have center faculty as mentors in many of these startups. And then we periodically organize various conferences and workshops and so on. So the research of the center, just want to show a few highlights. Maybe I'll take 5 more minutes. So this is part of what Professor Anil Prabhakar and his group does. Where they are building what's called a metro area quantum access network. Of course, this abbreviates to MACAN, which is nice. So IIT Madras is situated here, and we are very proximate to something called a research park, which in a way is a very nice ecosystem, because we now have a lot of startups and companies which get incubated there. And a lot of them today are, of course, very much interested in the quantum space. So there's a kind of healthy engagement between the research park and the faculty at IIT Madras. We also have this Center for Securities and Electronic Transactions. This is a government organization which is also interested in quantum key distribution and secure quantum communication. So we have set up a link of this kind, which we have now demonstrated and so on. And we are now under the National Quantum Mission, we are planning to expand this into a much larger network. The kind of protocols that we implement, for those of you who are interested, are phase-based protocols over fiber. We don't do polarization-based protocols. We rather do phase-based protocols like differential phase-shifted QKD, coherent one-way QKD, and so on. Let me maybe skip this since I already mentioned this, except I should say that IIT Madras is also probably the only institute in India which is a partner in the IBM quantum network. We've been a part of this since October 2022. So among the other research highlights that I will show, I'll also show a little bit about what we have done in using IBM quantum hardware or in collaboration with IBM as well. In terms of pure theory or fundamental theory, we have works like this, which have come out of our group. This is from Professor Arul Lakshminarayan's group, where they solved a major open problem it's a kind of math puzzle, if you will, which they are related to mutually orthogonal Latin squares, and they had a very nice new angle to it based on entanglement. And of course, in the quantum information theory context, this has connections to things like absolutely maximally entangled states, which then leads to error correcting codes, mutually unbiased basis, and all of that. We have a bunch of faculty that work on the quantum hardware with IBM, and then do try to realize applications using the access to quantum hardware that we have. This is from the group of Professor Chaitanya in chemistry, where they have tried to run some quantum chemistry algorithms. This is again from Anil's group, where in collaboration with folks from IBM research team in India, we worked on optimization and quantum machine learning problems. Then this is from Sanjeev's group in biotech, where they worked on protein folding. This last piece of work is from my own group, where my students came up with a new take on order finding. So this is some detail on that, which I can come to if any of you are interested, but I'll skip this. This is just to say that we have some amount of quantum algorithms and applications research going on here. So now, last 2 minutes, a little bit on my own research interest. So I work on something called noise-adapted quantum error correction. So, well, maybe to this audience, I don't need to say what is error correction or why we need error correction. But anyway, here I have a very simplistic picture of a system environment interaction. So we know that the qubits that we build today are not isolated. They are subject to this sort of unwanted interaction with the environment. They undergo what is called decoherence. And this is what we call noise. And this is today one of the biggest limiting factors in realizing the true potential of quantum computing, right? Now, while much of the error correction research focuses on what is called Pauli noise, which is, you may have heard of bit flip and phase flip or depolarizing noise. So these are all examples of Pauli noise. What my research team focuses on is sort of deviating from Pauli noise, looking at what is the true noise that's affecting the hardware. And one example of that is what's called amplitude damping noise. So for those of you who work with superconducting qubits, you will know that this is a very important, or maybe the dominant noise process today in, say, transmon qubits. This is what is often called a T1 process, and the coherence times that you see along with the qubits in most cases are essentially these T1 times, right? So how does one mitigate or protect information from this kind of noise? And this kind of noise is not really Pauli. If you look at these noise operators, they are neither of the X, Y, or Z type. So this is not really a Pauli noise channel. Of course, there are ways to deal with this, even with the standard error correcting codes. But what we try to explore is, can we do better if we design quantum error correction schemes tailored to these kind of noise processes? So this is an example of what we can do if we do noise-adapted QEC. What I have on the x-axis here is the noise strength, which is essentially the probability of this excited state dissipating down to the ground state with the loss of a photon, typically. So this is what is called the damping parameter, the noise strength. And what I have on the y-axis is the fidelity between the original qubit and the qubit after the effect of noise. In the case of this, linear fall is, of course, without error correction. And all of these quadratic lines are after error correction. And you see that the standard error correction picture will tell you that you need at least 5 qubits to protect a single qubit from any kind of noise. And this is the 513 code, which is in red here. But then we have these 4-1 codes, which are basically 4-qubit codes, which are able to achieve comparable performance or sometimes even better fidelities than the 5-qubit code. So this is an example to say that one may be able to come up with more resource-efficient protocols if one tries to design codes that are tailored to a particular noise model, which we know is dominant in the system, rather than go with the standard sort of stabilizer codes and so on. So I think I'll maybe skip all of this. It's maybe a little technical for this session. But maybe I will actually stop here. I'll just flash this last slide, which talks about the different sort of educational initiatives that we do related to quantum computing and quantum information. And maybe I'll stop here, and I'm happy to take questions. I have not put any information exactly on the Indian, how do I say, the processes here, or, I think there was some, in the email, I saw some things about funding and so on. Maybe I will take those as questions during the discussion. Okay. So thank you for your time, and I hope this was useful.
Yeah, so that was a wonderful talk. And especially I liked the discussion, technical part also. And that's a little bit new, but also interesting because I personally work on this T1 kind of thing on fabrication side. So yeah.
Sure, yeah.
So first of all, thank you for this talk. Now we are going to our next speaker,
Okay.
Professor Bhanu Dash. So Professor Dash, can you just share your slides, talk? Otherwise, we can also help if there's any issues.
Sorry, can you see my slides?
Yeah.
All right. So let me begin by thanking Dr. Opchen Banerjee and the members of SciROI for providing this opportunity to talk about our work at our center. And it's really a great initiative. I mean, I was not aware of it. And I was very happy when Dr. Banerjee wrote to me about SciROI and about the activities of SciROI. What I'll do is I'll just give you a brief overview of what our center is all about, its focus, and a little bit about the future outlook. So we are a brand new center. I mean, on paper it's 4 years, but in actual practice it's about 2 years. So we lost 2 years because of COVID. And I personally have been here for just about 2 years, worked long distance as the director from Japan for about a year. Now, in the past 2 years, we have 9 faculty members, 3 visiting faculty members, 2 visiting scientists. Well, it's all mentioned here. So we have a quantum engineer, 4 postdoctoral fellows, 10 doctoral. Actually, it's now 18 doctoral students, 5 project associates, and 2 research assistants. Now, about the vision and the objectives, we are both a center for research and education. So as far as research goes, we intend to carry out cutting-edge research, both in experiment and theory, in the field of quantum science and technologies, and in education to impart knowledge via high-quality education programs in quantum sciences and technologies. And we have an advisory board, an international advisory board, to advise us regarding our activities. And the names are mentioned. All of them are leading scientists in the field of quantum computing and quantum information. Professor Kenji Omori is very well known for his work on quantum computing of neutral atoms from the Institute of Molecular Sciences in Okazaki, Japan. And many of you probably know about Professor Arthur Eckert, who's at the University of Oxford and the Center for Quantum Technologies in Singapore. I mean, he has made very profound contributions to the theory of quantum information, quantum cryptography in particular. Then we have Professor Nakamura, who's the director of the Riken Quantum Computing Center and the University of Tokyo. He's the inventor of the superconducting qubit and a very close collaborator. So we've recently completed a project with him. And then we have Professor Hartmut Heffner, who is the director of the National Quantum Computing Hub in the US at the University of California, Berkeley. And he's a world leader in the field of trapped ion quantum computing. So we've had very productive interactions with all of them. And now I'll just mention the groups that we have at our center. We have a group on quantum computing and quantum machine learning. And the quantum machine learning component is rather new. And then we have a group on quantum information and communication. That's also new. And in quantum computing hardware, we have an experiment that is underway on superconducting quantum computing. I'll say a few things about that later. And we also have experimental activities in quantum sensing in two different platforms, actually three different platforms: NV Center, that's Nitrogen Vacancy Center, photonic integrated circuits, and cold atoms. Now, in theory, in quantum computing and quantum machine learning, the focus is primarily on atomic and molecular physics, with an eye to real-world applications like drug discovery and to probe materials for electric car batteries. And so we have collaboration with groups in different parts of the world. And our approach to quantum computing is twofold in terms of actual quantum computation. We access commercially available quantum computers, like IBM, for example. And we also have access to MITI. This is the Ministry of Electronics and Information Technology. So they have a national program. It's the first program of its kind in India to provide quantum computing to certain users. You'll have to apply for a grant, and if you get it, then you'll have access to various platforms, superconducting, trapped ion, and for some time quantum annealing through the cloud. So that's one kind of access we have to quantum computers. But another more fruitful approach has been to actually directly work with groups that have built quantum computers in their own labs, in particular universities. For example, we've had a very productive collaboration with Professor Nakamura, a 4-qubit quantum computer that he built at the University of Tokyo Riken. And now they've already built a 64-qubit at Riken. And so that has been a great learning experience. And more recently, we've had a very fruitful collaboration with Professor Mark Safman at the University of Wisconsin-Madison. And he's also the chief scientist for quantum computing at Inflection, which used to be known as Skoll Quanta. That too has been a great learning experience for us. You know, I mean, we sort of interact on a daily basis, and we tell them our requirements, and then they try to, build the circuits accordingly, and then we together plan how to do the measurements and so on. So, it's been very productive, and we've been able to, actually get to grips with problems on quantum many-body theory, which we thought will take decades, but it's moved faster than we expected. And we have collaborations with Okinawa Institute for Science and Technology on different aspects of quantum information and quantum computing, and with Keio University at the quantum computing, it's called the Keio Quantum Computing Center. It was the first IBM quantum hub in Asia. And the head of the chemistry division there is also a visiting faculty at our center. And together we have come up with a new fault-tolerant quantum algorithm, and we've applied it to look for excitation energies, which is not very common. It's much more common to calculate ground state energies. And we've also been very fortunate to have very productive discussions, interactions with IBM Research India, that is Dr. Venkat's group, and especially with Dr. Dasgupta. And in complexity and machine learning, we've have collaborations with groups in the UK, Japan, and in Italy. And as I mentioned, we also work on fault-tolerant quantum algorithms, particularly in collaboration with the KO Quantum Computing Center. And we also have come up with our own algorithms and applied it to condensed matter many-body problems, especially bosons in optical lattices. And we also have an effort going on quantum error correction. The collaboration is with the Center for Quantum Technologies, and more recently with the University of Edinburgh in the UK. And another very interesting area that we've been working on is the dynamics of physical systems. That is, it's also called Hamiltonian simulation, where you take a physical system and look for different quantum phases, which we've done, and we've looked at hardcore bosons, which can be considered as qubits, and we've been able to get different quantum phases. And classically, we've been able to get, we've been able to observe something called the Kibble-Zurek mechanism. That's, I'm being a bit technical here, but that's something which it's a very interesting dynamical phenomenon which happens when you perturb a system through some time-dependent interaction, and that develops defects, and they are proportional to some power of the time during which the system is perturbed. And more recently, I mean, we have started activities in quantum information and quantum communication. We've been very fortunate to have Professor Arun Patti, who's a world leader in quantum information, who's made many profound contributions. He's joined us recently. And so in the past 3 years, we've had about 30 publications, including papers, 3 papers in Physical Review Letters, Physical Review A, and scientific reports, Journal of Chemical Physics, and so on. So that's just a bird's eye view about our theoretical activities. A very important part of our work is the actual building of a superconducting quantum computer. I actually forgot to mention in the theory part of my talk that we also work on quantum annealing, which is the second type of quantum computing, and that's absolutely suitable for optimization problems. And we recently got the most accurate result to date on the D-Wave quantum simulator, where we calculated the fine structure interval. That's an atomic effect due to relativistic processes. We got an accuracy of 99%. By that, I mean compared to experiments in the lab, not classical computers. So on the theory front, we've been working on quantum annealing, and we have a very good collaboration with Kilimanjaro, a startup in a unique kind of a quantum tech startup in Barcelona in Spain. And together, we've got a grant from the European Research Council, and Keio University is also part of this work. Okay, so now about experiments, as I said, the plan is to build actually 2 kinds of superconducting quantum computers, both gate-based, a digital quantum computer, as well as a quantum annealer. A quantum annealer doesn't have gates, and it's very suitable, as I said, for optimization problems. So we've already acquired a dilution refrigerator, and I'll come to that in a minute. And in quantum sensing, as I mentioned, we work on 3 platforms: photonic integrated circuits, nitrogen vacancy center, and ultra-cold atoms. Now, one important aspect of our work on experimental quantum computing is to look for new materials that would serve as qubits. Now, currently, it's aluminium, which is widely used, but there are other very good candidates, in particular, cobalt disilicide. And our experimental group actually has carried out measurements even before we could set up a lab at the Shah Institute. And they observed superconductivity in cobalt disilicide. And, as I said, I mean, this is still early days for us. So we just have a single qubit. And I've just mentioned some of the characteristics that we've measured for the different qubit and coherence dephasing times. Okay, so those of you who have some familiarity with superconducting quantum computers can get an idea of this. All right, so now we have been working on both photonic integrated circuits and nitrogen vacancy centers for the past year and a half. And we've been rather fortunate to have collaborations both in India and outside of India, particularly with Professor Dmitry Budkar, who's at the Helmholtz Institute in Mainz and also at the University of California, Berkeley. So he's been a very old collaborator of mine on atomic physics problem, but he also works on nitrogen vacancy centers and magnetometry. And that's where our focus is. And we've also been collaborating with groups in India, particularly Professor Kasturi Shah from IIT Bombay. And we've also made some progress in photonic integrated circuits. There we have collaborations with groups both in India, Singapore, and the US. In US, it's with Professor Majumdar at the University of Washington, Seattle. So that's quantum sensing for nitrogen vacancy, excuse me, nitrogen vacancy center and photonic integrated circuits. Now, another line of work on experiments is based on cold atoms. Now, there's a lot one can do. And in fact, neutral atoms are one of the leading candidates for quantum computing. But our effort is rather modest. I mean, maybe 5 years from now, maybe we can contemplate thinking of doing a neutral atom quantum computing experiment, but that's rather far into the future. So what we have been doing is trying to sort of build a cold atom-based gravimeter. So this is for measuring gravity in different situations. And this also has a lot of real-world applications, which we are, which we plan to do in the future. So this is something that's been well funded. I mean, apart from within our center, from different research agencies in India. And as I said, the name of a center is Center for Research in Education and Science and Technology. So education is a very major focus of our activities. And clearly, I mean, we'll all agree that there's a symbiotic relationship between research and education. And we therefore have already started a PhD program. It started in collaboration with IIT Tirupati, but now it's with what is called ACSIR. For those of you who may not be familiar with ACSIR, it stands for the Academy of Scientific and Innovative Research, and it's one of the centers within CSIR. That's the Council for Scientific and Industrial Research, and they can award PhD degrees. So they've recognized us as a center, and so our PhD programs are actually carried out through these two places. I mean, primarily ACSIR. And well, I mean, the first 2 years, we got 12 PhD students, and now this year, we will take 6 students. It's difficult to handle more than that at the current time. And we have an absolutely outstanding international student from Cameroon who had studied at the African Institute for Mathematical Sciences and is doing absolutely outstanding work on quantum computing. And we'll soon have master's programs on quantum computing, quantum information and communication, as well as quantum sensing. And we've had a lot of requests from various places in India to launch certificate courses. And I think we will offer them in the next few years. It could be even as early as next year. So this, in a nutshell, is what we've been doing. And regarding funding, our funding comes from primarily from the TCG, CREST. CREST stands for Centers for Research and Education in Science and Technology Foundation, which is based both in the US and India. And we have funding, as I said, from the European Research Council and some from within India. And that's, it's just starting to happen from Department of Science and Technology, DRDO. We're expecting grants from ISRO and so on. So we welcome applications in these areas, the areas that I mentioned, which are quantum computing, both experiment and theory. I think we would particularly welcome experimentalists because it's not very easy to find trained experimentalists in the field of quantum computing in India. So if you have a background in that, you're most welcome. You're very welcome to visit, spend some time, or apply for faculty positions or postdoctoral or whatever. As I mentioned, we have ongoing programs on quantum sensing in the 3 different platforms that I mentioned. And we would welcome applications in those areas too. And quantum computing and quantum machine learning, that again is something that we are very committed to. And that's an area that will certainly grow in the future with collaborations with groups in the US, Japan, and Europe, and partly Singapore as well. So I think I should stop now, and thank you very much for your attention, and I'll be happy to answer questions that you may have.
So thank you, Professor Dash, for such a nice talk, and this is really a great new initiative. So now probably we should
move forward, Archana, sorry, just a reminder to the audience that we'll be taking questions at the end. We're not taking questions after each speaker.
Yeah.
So if you can already start posting questions on the chat, if you have some questions from Professor Mandayam's talk or Dr. Das' talk. And also, I think we should do our first poll questions, right? Nitin, can you
Yeah, we
please
should.
release the poll questions before we move to our next talk?
Okay, so probably this the poll will be available now. So by that time,
Yes, sir.
probably we should move towards the next speaker.
Wait for a moment. I think like we should wait for the poll to end. I think it will end soon.
It will end soon.
Yeah, it will end soon. Maybe we should
So
wait
yeah,
for
I'm
a
just
couple.
waiting for like people to respond. It's if people want to respond, it's 18 people have responded so far. So anyways, I think that's it's kind of
50-50.
almost half and half.
Yeah. I think yeah, we can now move to our next speaker, Archant, please.
Okay, so now I will invite our final speaker, Dr. L. Venkata Subramaniam, who is lead of IBM Quantum India. So please, Dr. Subramaniam, please, can you share your thought on this topic?
Thank you. So I'm really happy you invited me to be part of this panel along with the eminent professors Prabha Mandyam and Professor Bhanu Das. So thank you. I'll have some slides I want to show you. Okay, I'll try to share.
I think
Get them out.
Dr. Das, can you please stop sharing your screen so that Dr. Subramaniam can share his screen?
Okay,
Okay,
sorry,
Yeah.
thank you.
sorry about that. Yeah.
No worries.
Okay, are you able to see my screen?
Yeah, yeah.
Okay, great. So I'll start with a poll of my own. Okay, so there is a react button at the bottom. Please put thumbs up or thumbs down. Okay. So how many people here know that you can access a quantum computer over the cloud? Thumbs up if you know, thumbs down if you don't know. Are you doing it? So there is a react button. Okay. The second question is, where do you think the talent in quantum today is residing? Those for US, those for Europe, Japan, India. Okay, these are some questions we'll answer as we go along. Okay, so keep them in mind. So we all know, quantum computers, there have been a lot of promises that have been made, whether it is in efficient energy storage, whether it's in optimization problems, whether it is in drug discovery. So there's a lot of promise. People have, there have been some early results also, even on the current quantum computers. So what we are seeing is that the hardware is now improving and allowing us to do experimentation. And I'll talk about the IBM utility experiment very briefly. But at the same time, what we are seeing is that the algorithms are also, improving further and further. Okay. So both of these are happening simultaneously. And so this is, what we are saying is right now we are in this utility era, and we are now moving very fast towards quantum advantage. So what is quantum advantage? Quantum advantage is where you will be able to solve a problem using the current hardware, using an algorithm for quantum where you are able to do something much faster, much more efficiently using the quantum computer compared to what you can do classically on a real business problem. Okay, not on a on a real business problem. So this was the 2023 paper where IBM showed that a noisy quantum computer produces accurate expectation values on 127 qubit systems and does much better than brute force classical computation. So anything that you can do with simulation, you can do much better with this. And since then, there have been multiple papers which have shown that, not from IBM, these are from various other universities across the world. And I'll talk about one from India also briefly. So this has been, in the past, so this paper came out middle of last year, and in the sort of 1 year or less than 1 year, we have seen a lot of new papers come out which use 100 plus qubits and hundreds or thousands of gates, okay, to solve problems where you're demonstrating, sometimes or often you're demonstrating that you're doing much better than what you can do using the best supercomputers for simulation. Third thing that is happening is that IBM is delivering what we are calling as quantum centric supercomputing. Okay, so where we are saying is, you're combining the power of classical with quantum and trying to solve things which go beyond what you can do classically, right? And this was a recent paper we did with Raiken, where you ran these classical distributed calculations, which served as the pre-process to big classical data coming from a chemistry problem, right? So typical classical quantum workflows today have used some limited amount of information transfer between quantum and classical, and where basically you're estimating the expectation values or the circuit parameters. And in this case, what was done was you transferred all the raw quantum data to a classical cluster and then use it in the most expressive manner so that you can obtain the lowest energy possible. So this is sort of the, so what we're now saying is that hardware is progressing and we're not seeing any roadblocks to what we have promised, which is, 100,000 plus qubits by 2033. We have entered what we are calling the quantum utility era, where we are able to show that using 100 plus qubits, using 100 and thousands of gates, we are able to do much better than estimates than brute force simulation. And we are also saying that, to maximize searching for quantum advantage, we now have developed a new form of computing where we are saying that we are bringing together classical and quantum into what we call the quantum centric supercomputing. And this is being, used in several now industrial applications, 3 classes of them: simulating nature, mathematics and processing data, search and optimization. And this is now being used across industries, and IBM has 280 plus partners, and several of these industries are using these to actually try and solve real business problems. So for example, Cleveland Clinic, Woodside, ExxonMobil, Boeing, and there are some which are now coming up from India too. Okay, so in the next round of slides that we will be showing, you'll have some examples coming from India. Okay. So this is, like Prabha ma'am said, we are working very closely with IIT Madras. And one of the problems that we jointly worked on was the protein structure prediction, where we again used a 100+ qubit system to predict how protein structures form, right? So in this example, as you see, if you do a wrong fold, instead of ending up with that beautiful rose, you end up with a crumpled piece of paper, right? And that's the same thing, you want to see how proteins fold in 3 dimensions. And this was work which we did, my colleagues did, I did not do. I'm just highlighting it here as one example of utility scale computing that is coming out of India today. Okay, so you're doing things over both classical and quantum in a quantum centric supercomputing way. And as I said, this is what you're going to see more and more going forward, right? So what I'll also talk about is, there is the National Quantum Mission, where both IIT Madras, TCG Crest, and several other universities in India have also been participating. There were calls which came out in January. The submissions were completed in April. And what this has done is it has, generated significant interest from both academia, industry, startups, the whole ecosystem. What has happened is this has also now been being monitored at the highest levels of the government, right? There is huge interest at the highest levels to make sure that the money that gets invested is utilized and it leads to India becoming a leader in the quantum computing area. And of course, media has been tracking it, and it has reported almost every development that has happened. But to the question I asked, where is the quantum talent today? So what we are seeing is that on our IBM systems, we are seeing huge uptake from India. 200,000 people downloading the study material, joining our classes. Some of these are much bigger than what we are seeing even within the US. Okay. And this is the McKinsey report 2023. As a single country, India has the largest number of graduates in quantum technology. And this is something, as I said, we are observing on our systems. Okay, the IBM systems, the free systems online system is broken up into 20 queue slots. And as you can see here, this is the top 10. The top 10, just the top 10 have used more than one system completed that, So, and this map that you see, people across the country are using these systems. And this is when there are maybe a handful of colleges in India teaching quantum computing. How many are there? Less than 10 today that offer quantum computing courses. But still, we are observing that, the talent here is immense. It is bigger than anywhere else in the world today. And these people are actually, these are the free system usages. And as you can see, there are these clusters in Kolkata, probably helped by the work that TCG Crest is doing. And this is just the free systems. Okay, I'm not counting the paid or the premium access, for example, that IIT Madras has. Okay, so those are also, going up, much bigger than anywhere else in the world. Okay. So what this means is there is a huge opportunity right in front of us here in India. Okay, and I, as the quantum lead for IBM, my goal is to shift the center of gravity for IBM towards India. Okay, and we have been growing our team here. Tens of people now getting hired. And as I said, my goal here is to make sure that at least the IBM work, a lot of the quantum work shifts to India from everywhere else in the world. And for that, of course, we need the help of the, the the universities here, TCG Crest, IIT Madras, and this whole ecosystem, which is showing that there is huge amounts of talent which is already present here. Okay. And IIT Madras is the first quantum innovation center in India. Okay. And there are 40 across the world. And so Prabha ma'am showed a lot of the work that they're already doing, and great work. And some of that I also highlighted, that utility scale paper or the work that we've been doing with Professor Sanjeev Senapati at IIT Madras. Okay. So now, there are these, at least there are 4 working groups that IBM has formed. Well, these working groups are not run by IBM, but they are run by universities and industry partners. There are 4: optimization, materials and HPC, high energy physics, healthcare and life sciences. Of course, I invite those who are interested to join these working groups. But also, our goal here is to start a working group in quantum machine learning out of India. Okay, so I will invite Professor Bhanudas, Professor Prabha Mandyam, and others, not just for India, this is across the world, of course. All these working groups get formed by partners across the world, and then they sort of publish this position paper. Okay. So if you go look, you'll find these 4 position papers in these areas. And our goal now is to start a quantum AI led out of India. And as I said, we will need all the help we can get from the professors on this panel and others also, and industry. We are seeing a lot of interest from Indian industry also now for looking at quantum computing. And given that there has been this national quantum mission which has come up, there is this huge interest to look at how quantum computing can help their industry, the industry here in India. So what we need is, we want to transition to quantum advantage, and this is going to happen. It's going to happen very soon. As I said, we are already in quantum utility, and the next step is quantum advantage. But to do this, we need a dedicated community of industry researchers and users to activate this discovery of algorithms. So when internet started, okay, when PCs started, what happened? Microsoft came, internet came, Google, AI, ChatGPT. With quantum, we believe that that company for quantum is going to get, that one or many companies in quantum are going to get formed in this decade. And are those going to come out of India? I mean, in AI too, we had a lot of talent, but we haven't seen those big companies come out of India yet. But in quantum, the goal of the National Quantum Mission, the goal of IBM, and I hope the goal of everybody else here in the Indian ecosystem, is to ensure that, this company, the big quantum company, comes out of India before the 2030, when it's expected that these will start forming. So with that, I'll stop here. I just wanted to give you an overview, and yeah, of course, we can go into the discussion now. Thank you.
Hi. Okay. Thanks for sharing your thoughts, Dr. Subramaniam. Archan, can we go for our next poll question, and then I think we can
Yeah.
move towards
yeah.
the Q&A.
Yeah, exactly.
So our next poll question is now live. Please share your thoughts. Okay, so it seems that there is a good amount of distribution among people who are already working in this field or who are interested in working in this field. So I hope you will get a good discussion if you're really interested in working this field, and you can learn from all our panelists and you can ask questions. Again, as a reminder, please ask your questions over the chat box, and we'll share or we'll ask those questions to our panelists as soon as it is possible. So I can already see that some questions are coming up. Archon, do you think we can start with the questions from the participants, and then
Yeah, I think so. That will be
in
good, I
between we
guess.
can ask the questions from the volunteers?
Yeah. So I can't. Let me see the questions. Can I? Oh,
Do
yeah.
you see those questions?
Yeah.
I can ask
Yeah.
the first question.
First question, if you can ask. Yeah.
Okay, so it's from Anukrati, is a PhD candidate in neuroinformatics at the University of Toronto in Canada. So she is interested in learning more about the emerging trends in India on the intersection of quantum science and neuroscience, and looking for possible collaborations in the future. So she's saying, like, if any of the panelists can guide her about it based on their experience. So if anyone can chime in.
Okay, so sorry, I'm not aware of anybody who's working on quantum science and neuroscience. I know individually people working in both of these areas, but not somebody at the intersection of it.
Any more thoughts from other panelists?
Yeah, let me just say a few things. I mean, I'm a physicist. I'm an atomic and molecular many-body physicist. And to the best of my knowledge, I could be wrong, there's no one actually working on quantum science and neuroscience at the intersection of these areas. But there could be people working on other aspects of biology. I mean, drug discovery is something which interests us and other groups. Interestingly, you know, one of the centers within TCG GREST is on neuroscience. It's the acronym is CHINTA, Center for High Impact Neurosciences or something like that. So we really haven't talked, you know, we've just had general discussions, but not really talked about applying, quantum to neuroscience. But I think that's a very interesting area. I'm sure, you know, I mean, there's been a lot of work on computational neuroscience, that is using classical computers, in particular at the National Center for Biological Sciences in India, in Bangalore. There is a computational neuroscience group, but they probably have not considered working on the quantum computing aspects. But it's a very interesting problem. And I would be happy to support that. I mean, if there is someone with a neuroscience background and is willing to try to use quantum computing, I mean, I would be very supportive. And, you know, I mean, if we could even initiate such an activity in our center, and so the person who would like to lead such an activity in our center, will have our support, which is quantum computing and other aspects of quantum information, and also the support of our neuroscience center. But there could be places in India where they may be considering working at the interface of these two areas, but I am not aware of that.
Yeah, if I can just add a little bit to that. So if I interpret the question a bit more broadly as the interface of quantum and, let's say, the biological sciences. So quantum biology is something that people have been thinking about and talking about. And one area where people in India do look at is the role of quantum coherence in biological processes. So if I interpret the question sort of more liberally like that, then Professor Subhashish Banerjee's group in IIT Jodhpur, they look at quantum coherence, for example, how that helps birds navigate, or how that helps photosynthesis, or how that helps complex biological processes, the role that quantum coherence plays in that. So I think there are groups essentially that look at quantum dynamics of various forms, which may also be interested in this. Specifically neuroscience and quantum computing, like others have said, I do not know of this thing. But again, the other area where quantum computing and biology overlap is in solving problems like protein folding, drug discovery, and so on. So that we have groups in IIT Madras and NCBS and so on that look at these things jointly with the IBM team, of course. Yeah.
Okay.
Cool.
Thank you everyone
So
for sharing. Okay, yeah, Archana, you can ask the next question. I think
yeah,
it's
so probably we can ask one question from volunteer side and then go pick one question from the chat again.
okay, sure. Yeah.
Yeah. So one question we have is that suppose I am an early career researcher, like starting my PhD or starting my postdoctoral journey, or even before that. So what kind of relevant courses or what kind of skill sets should I focus on to grow as a quantum research scientist or quantum engineer to grow? Yeah, that's my question. So if you can give some advice.
Sorry, could you ask the question again, please?
So suppose I'm an early career researcher who is starting my career as a PhD student or postdoctoral researcher or even earlier. So what kind of courseworks or what kind of skill sets, like technical or experimental skill sets, should I focus on so that I can grow in future as a quantum research scientist or quantum research engineer, this kind of role?
Okay. Thank you.
Yeah, I could start off. So from the theory side, like if you want to become a quantum information theorist or a quantum computing theorist, then certainly a background in linear algebra or a certain comfort and knowledge of linear algebra becomes very important. Then, of course, there are sort of the basic courses in quantum computing and quantum algorithm and familiarity with all of that. People come in from diverse backgrounds. So if you already have a physics background, then you probably know a certain amount of quantum mechanics. You probably know a certain amount of linear algebra, but typical physics programs do not cover the kind of linear algebra or the extent that you need to know to become a quantum computing theorist or a quantum information theorist. If you come from a physics background, then you also perhaps have not done courses in information theory or complexity. And it is sometimes useful to have a little bit of knowledge of that. So I myself did a course in classical information theory, which I have found to be useful later on. So during my grad school, I did a course in the electrical engineering department on quantum information theory. I find that to be useful, gives you a useful perspective if you come from a physics background. Conversely, if you come from an electrical engineering or a computer science background, then a course in quantum mechanics will be useful for you. If you are interested in the experimental aspect and the devices and that sort of thing, then I would say photonics, courses in quantum optics, photonics, and courses on superconductivity. So for example, we have a master's level course in IIT Madras on superconductivity, right? I think these or a course on atmol physics, right? These sort of courses, I think, are useful for understanding how one may build a device that truly performs or stores quantum information or performs quantum computing. So that, I think, is my take on it.
Thanks. Any other speakers can have any comment?
Yeah, I mean, I would say that the starting point should be quantum mechanics. You know, I mean, and certainly the matrix mechanics approach to quantum mechanics, which, as Professor Prabhamandian said, you know, is linear algebra. I think a strong grounding in that area is essential to understand quantum computing. And of course, you know, I mean, the more mathematics one knows, the better it is. You know, linear algebra is, in a sense, the mathematical basis of quantum computing. But other you know, techniques in mathematics will also be very useful. And a knowledge of basic computer science, you know, and is also useful. I mean, that's something that I lack. I'm a physicist, but many of the younger physicists, you know, have ventured into computer science. And I was just talking to a friend of mine today in Singapore, a young friend. And, you know, I mean, he's recently, in the past 4 or 5 months, he works on quantum computing, quantum machine learning, quantum error correction, and so on. So he's published 2 papers in Physical Review Letters. And he has, you know, his papers have recently been accepted in leading computer science conferences. I think he told me it is FOCS, FOCS, and STOC. You know, I mean, you know, he's much younger than I am, and so you know, so he, you know, I mean, age is not a problem, but you know, it's just your mindset, your attitude, actually. So knowing both these areas well. Basics of quantum mechanics, especially the matrix mechanics approach, and the basics of computer science, I think is certainly, I think these are prerequisites for doing research in quantum computing. That is the theoretical side. Now, experiments, of course, that's a different kettle of fish. And I think Dr. Achan Banerjee can comment on that much better than I can. I mean, but I'll tell you what I have been hearing from my colleagues. And I work very, very closely with experimentalists, you know, primarily in the US with Professor Mark Safman, who's a pioneer in neutral atom quantum computing, the first person to build a neutral atom quantum computer at Wisconsin and then in Cold Quanta. And Professor Nakamura in Japan, and you know, many of my colleagues in Japan. There, I mean, what I hear is that it's you know, not only important to know quantum mechanics and physics, but also engineering. You have to be good with your hands. Now, very interestingly, a lot of the very important quantum computing experimental work in the US is done in electrical engineering and computer science departments, you see. I mean, for example, Professor William Oliver at MIT, he's primarily in the electrical engineering department. And that's, you know, I can mention many others. You know, I mean, you know, Chuang, for example, Isaac Chuang at MIT, his primary appointment is also in electrical, you see. So I guess it seems to me that if I compare India and the US, the people who are working in India have a different kind of outlook and different kind of training than the experimental groups in the US, where a lot of, you know, I'm just named, you know, 2 senior scientists, but there are a lot of young people in various universities. I mean, just 2 days back, I was talking to a young scientist at the University of Washington and she's in the electrical engineering department, and doing trapped ion research. So, I mean, I'm not the best person to give advice on what skills one should have for experimental work, but it seems like a knowledge of both physics and engineering, especially hands-on experience, will be very useful. And of course, as I said, there are experts like Dr. Banerjee who can, answer this question much better than I can.
Yeah, thank you, Professor Das, and especially you mentioned the experimental skills and hands-on skill. I mean, that's a very important part. Also, Professor Subramaniam, do you want to just make some comment?
Yeah, I think everything has been said. All I'll say is that the physics students need to work on their programming skills. The CS and the electrical engineers need to work on their quantum mechanics and the physics background. Okay, so that's very important. Also, what I think is, people today, even though there are free quantum computers available, they seem to be discounting it. And I want to just point out, the quantum computers are like the microscope in the year 1600. Okay, there was biology research before the microscope also, but after the discovery of the microscope, it accelerated biology research by leaps and bounds. Okay, and the same thing is going to happen now that quantum computers are available. So irrespective of what you are working on, whether you're an experimentalist or you're a theorist or whatever you are, make sure you are able to use this quantum computer. It's the same in AI also. In our offices, at least in IBM, people who know AI are replacing the people who don't know AI. And it's the same, here also. Just pick up whatever tools are there, learn to use them first. After that, you can build your own expertise on top of that.
Thanks. Sean, can you take a question?
Yeah, so this is from Santas Nayak. So he's interested in knowing that how the area of photonics will be helpful in quantum computing and quantum communication. If anyone can share their thoughts.
It's a general question, but if the panelists can comment something on that.
I mean,
So I'll just
photonics.
start. Yeah, sorry.
Oh, I'm sorry. Please go ahead. Please go ahead. No, I'll be brief. I mean, photonics is important both for quantum computing and for quantum communication. I mean, it's the backbone of quantum communication, photonics. So I think good understanding of various aspects of various quantum aspects of photonics. I mean, you can think of it as quantum photonics, quantum optics, photons or whatever. I think that's really a very important area in the whole field of quantum science and technology. Again, like in many of the other areas, I mean, India is not in the forefront. I mean, it's growing. I mean, I know some groups, working in this area. I mean, others can comment on that. Others, panelists from India. Recently, I happened to visit Indian Institute of Science, and I was very happy to see that a young scientist, C.M. Chandrasekhar, who I knew was a theorist. I mean, I had met him when he was a postdoc in Japan, but he also has very good experimental skills, and he's trying to build a photonic quantum computer at the Indian Institute of Science. And he currently has 6 qubits. And I think in due course of time, I mean, he'll be able to do some kind of quantum processing.
Yeah, Dr. Subramaniam. if you want to share
I
some
was
thoughts.
just going to say that in IBM, there was a point where we were building bigger and bigger processors. Okay. Now the next phase is where we are going to interconnect these processors using photonic qubits. Okay, so you have a superconducting chip, and the interconnects between these are going to be photonic. So there is a convergence of photonic superconducting also happening as we go along.
Okay, thanks for all the thoughts. Do you want to go with the next question, Archon,
Sure.
from the volunteer side, or?
Okay, I can go from the volunteer side. So this is from the regarding this funding. So can you give some insight about this funding and collaboration opportunities, especially for new faculty members who are planning to start their group, especially focusing on this quantum science and technology domain?
Yeah, I could start, and then I'm sure to miss some points, so the others can pitch in after that. Yeah, so today I think is a very good time to be a quantum computing, quantum information scientist or engineer in India, because as you know, the National Quantum Mission is truly underway. As Dr. Venkat mentioned, the call for proposals is done. Various presentations have been made, and the funding mechanism is going to kick in very soon. And we expect that while there may be existing big groups which get sort of get to form what are called hubs in the field, but these hubs will then have funding which they will disburse. There will be several calls for proposals is what we expect for specific technical areas, and then funds will be distributed for these technical areas. Probably Venkat will pitch in with some more details on the mechanisms and so on maybe. But the bottom line is there is funding for quantum today, and the NQM is one of the primary mechanisms by which we expect this will happen. But there is also, I think I had mentioned in my slides, and Professor Bhanudas also mentioned MEITI, which is the Ministry for Electronics and Information. I forget the expansion exactly, but MEITI also funds quantum, not just quantum communication research, but also quantum computing research. There are other organizations like the DRDO, etc., which are very much interested in funding both quantum computing and quantum communication projects. So today in India, I think, so I don't know, for those of you who are outside, if you're hearing the words quantum winter is something that I hear from my collaborators in the US and so on. And I often tell them that in India, we're just seeing the beginnings of the quantum spring. We are even yet to see the quantum summer, according to me. So I think the quantum spring is well and truly here in India in terms of funding. And as Venkat also mentioned, there's a lot of industry interest today in quantum computing in India. So a lot of whether it's the big majors like TCS and so on who are interested, or smaller startups, smaller niche tech companies, whether it's Nagarro, Emphasis, LTI, they're all interested in training their workers in quantum computing, in collaborating with academic institutes and funding quantum computing research in academic institutes. So today, as a physicist, as a theoretical physicist, I do not expect myself to be talking to industry folks, but the interest levels in India today are such that I often find myself talking to a lot of industry folks on quantum computing and quantum algorithms today. So I think really funding opportunities are galore in India at this point. But I also want to mention here quickly just a couple of things which about academia in India, at least. In contrast to academia, let's say in the US, for example, our funding requirements are actually very different. Our PhD students get funded by our own institutes for the most part, or by government fellowships, MHRD, and so on. So often I don't need funding for my PhD students, unlike a typical boss or a PI in the US who has to have a grant to be even able to fund their own PhD students. I do not need funds for my PhD students, at least definitely not for 5 years or 6 years in many institutes. If it stretches beyond that, maybe you need some funding. I do not need even to fund my student travel, which often gets covered. My students get to go to international conferences, again, funded by my institute or funded by MHRD-based travel grants, right? So at least as a theorist, then my funding requirements really boil down to, do I want to hire additional staff? Do I want to have a mechanism, let's say, to access quantum hardware? Do I want to buy GPU clusters, et cetera, et cetera? As an experimentalist, of course, I need to buy big equipment and all of that. But a lot of the funding requirement in Indian academia setting actually is eased out by the fact that we don't need to fund our PhD students. We even don't need to fund some of our postdocs. There are institutional mechanisms to fund postdocs. So in that sense, a lot of the, let me say, stress of grant writing, which I see a typical American or European PI go through, is reduced in the Indian context. But this is general, not just to do with quantum computing and so on. But yeah.
Anyone
Professor
else?
Dash.
Sorry, yeah. Let me start a few things. Yes, indeed. I mean, National Quantum Mission offers unique opportunities. And those of you, who may join later could still be part of the National Quantum Mission if you know some of the scientists working in this area. There are possibilities of joining later as spokes or spikes and so on. In addition, one can get funding for quantum activities. I mean, that's across the board. Computing, communication, and sensing through the Department of Science and Technology. The government of India is coming up with a new science body, somewhat comparable to the National Science Foundation. It'll be called the National Research Foundation, or actually Anusandhan National Research Foundation. That's not yet in place, but it will be the premier research funding body in India in the future. So there will be opportunities independent of the National Quantum Mission, and specific departments like DRDO, the Defense Research Development Organization, and ISRO, the Indian Space Research Organization. They also fund work on quantum. And I should also add that there are two more new national quantum missions coming up. Two more national missions coming up. One is the National Supercomputing Mission, which will be driven not by DST, but by MeitY. This is the Ministry of Electronics and Information Technology. So the supercomputing mission, the focus will be to build an exascale computer. There are very few of those in the world. And CDAC, the Center for Development of Advanced Computing, will take the lead in that. And one of the approaches that Dr. Venkat mentioned, which is what he called quantum-centric supercomputing, which is basically hybrid quantum computing involving quantum computers and high-performance computers, classical computers. That will be also a focus of this mission, the National Supercomputing Mission. And what I've been told is that the amount of money is about 4 times as much as the National Quantum Mission, you see. And there's another mission which actually has, from what I gather, has been accepted by the government, which is called the National AI Mission. There, the money also is a bit more than the National Quantum Mission. So, excuse me. So quantum is possible, through all these new missions that are coming up, particularly the National Supercomputing Mission. So there are certainly, I would say, good funding prospects when one thinks of all the possibilities besides the national quantum mission. And I should also add that in India, there are possibilities of funded foreign collaboration. And in the past, before I got into quantum, I'd been the recipient of many such grants, the US, Germany, Hungary, France, lots of them, in the 25 years that I worked. And those are still on. In other words, there are bilateral programs, say, for example, between the DST, Department of Science and Technology, India, and the National Science Foundation. One can apply for collaborative projects. And the amount of money is not large. It is sufficient, especially in theory, it is sufficient to carry out a productive collaboration. They cover travel from both sides and also the per diem, the daily expenses. So if the scientist from India goes to the US, the daily expenses, that is the living expenses, will be covered. And the same applies when the US scientist comes to India. And these bilateral programs, are with most of the European countries, Japan. So that is sufficient to initiate a collaboration. But if you're looking for a lot of money, equipment, and things like that, the only, there are very few such funding agencies. So there's an organization called CEFIFRA between India and France. They give some modest support financial support for equipment. With DFG Germany, there's again a little bit of that. And I think there's another organization called India-US Science and Technology Forum, IUSSTF, and I have received funding from them for a variety of things. And that again is like the bilateral programs. It covers travel and living expenses. But if you're a theorist, that's good enough not only to initiate, but even sustain a collaboration.
Thank you, Dr. Das. I think in the interest of time, we'll move to the next question and we'll finish up the questions from the audience first. So this is a bit technical question, so I'll go slow. So the question is from Anuj Merhotra, and the question is, while the transistor count in integrated circuits dominates discussions around Moore's law, do you think we must also consider the minimal increase in cost as quantum processing units advance? Balancing performance gains with cost efficiency becomes crucial for practical adoption. This is a very large question.
Okay, I can just start, okay, which is that today the per qubit cost for superconducting or many of the technologies is about $10,000 per qubit. How much should it be to be, like Anuj has mentioned, to be cost effective? This has to come down to about $100 per qubit. How is that going to happen? It's going to happen through using CMOS control technology inside the fridge. Today there's all that wiring which goes all over the place. The control circuitry is very complex. What you need to do as you pack more qubits into that fridge, you need to make sure that your control circuitry moves to 2 nanometers, which is less heat dissipation, all of those aspects. So there is the National Quantum Mission goal is also one of the goals here is to reduce the cost per qubit. The research and development is to do that. You've all seen IBM processor going from 20, 30, 40, all of that. But as it scales to that 100,000 mark, IBM isn't the one that's going to bring down the size and cost per qubit. It's going to be the research and development community across the world. And there is a big opportunity here in India to build those components. We aren't traditionally a hardware nation, but here is an opportunity to pick up parts, maybe the amplifiers, maybe the control circuits, maybe the design of the CMOS circuitry, all of that. We need to pick our things right based on the strengths of people who have submitted to the National Quantum Mission. And as you rightly pointed out, bring down that cost. And it has to happen within this decade, and it's going to happen within this decade. Who does it is the question. And so I think there is an opportunity here.
Any more thoughts? Okay. If not, we'll move to the next question again because we are closing towards the end. So the next question is from Santanu Saha, and his question is, he's interested in learning about the emerging trends and current capabilities in the domain of applicability of quantum computing on material science, large-scale simulations. Anyone can pitch in.
So when you say large scale simulations, so I take it you're not thinking from an experimental point of view, right? I mean,
I guess so, yeah. Or so
Yeah.
simulations is from modeling point of view, not
Yes. Now again, on material science, quantum computing and material science is still a new area in India. But there are people who plan to work in this field. I mean, one person who I know intends to work in this, partly in collaboration with us, is from IIT Delhi, material science. I mean, he has a strong background in theoretical atomic physics, theoretical material science in particular, density functional and embedding theory. But this area is still new in India. I mean, when you actually simulate materials using quantum hardware, quantum computers. But I think it'll grow. I think if I mean, the capabilities are immense, of course. I mean, with the current day, quantum computers, you can do some very interesting quantum simulations. I mean, the person I can think of is from the University of Chicago, Julia Galli. I mean, she's done excellent work. That is Galli, Julia Galli. She's in the chemistry and physics departments. She's done excellent work simulating materials using quantum algorithms, both near term, that is NISQ algorithms, as well as some fault tolerant. So there's plenty of scope, but it's still early days in India.
Okay, thank you for your thoughts, Dr. Das. Do you have any more thoughts on that?
So a lot of the work with IBM, the customers do is in the materials domain, whether it is new materials for batteries, new materials for new LEDs and things, the photo devices, whether it is for these solar panels. So all of this is materials work, and that's one of the most commonly used application areas for quantum computing today.
Okay, thanks for your thoughts, Dr. Subramaniam. We'll probably move to the next question now. It's a bit generic questions. It's from Samparko De. So they're saying like they're starting their PhD journey this year and will be working in the field of quantum computing and information. The question is, what could be a potential good topic for an electronics engineer for an impactful research work? I know it's a very generic one. If you can quickly
Yeah,
share
that's
some thoughts on that.
quickly generic.
So I think in a way, Dr. Venkat already answered this question when he was talking about bringing down the cost per qubit, right? So I think the electronics engineers are going to play a huge role. Uh, so I think what we need today to really scale up these quantum devices are quantum engineers, right? Who are able to optimize the control electronics, or able to optimize how this little chip, which needs to be refrigerated, interfaces with the control electronics, with the amplifiers, with your, the read in, the read out, and all of that. So I think that is where the next innovation has to happen, and that is what is going to help us scale up these things. So I think there's a lot for any electronics engineer to do today, and that's just in computing. So if I think in terms of communication, then I know that FPGAs play a huge role in any simple QKD link also. So I think from the communications perspective also, we need a lot of electronics engineer support in building and realizing quantum networks, quantum repeaters, and all of that.
Thank you for your advice, Dr. Mandyam. Do you have any more thoughts on that? Or otherwise, we'll move to the next question.
I mean, just very quickly, you see the name of our center is Center for Quantum Engineering. So, engineering is really very, very important for all areas of quantum computing, communication, sensing, and so on. I've sort of touched on this earlier when I said that you should have strong experimental skills, engineering skills, hands-on skills, so I really can't add anything more to it. I mean, I'm sure Dr. Banerjee can answer this question much better. But I could just suggest that, you could contact Professor William Oliver in the Electrical Engineering and Computer Science Department at MIT. I mean, he is very easy and very accessible. So I think, he can give you excellent advice if you're looking for general advice.
Thank you, Dr. Das. We have one more question from participant. It's again a very generic, and in terms of the opportunity of quantum degrees, major and minor in private universities in India, and how it can be promoted for attracting students towards that degrees, and how industries and any premier educational institutes can support that.
I think a very good example is TCG Crest, right? It's really a private institution, and Professor Das can say how they made it successful.
Okay, thank you. I mean, yes, I do have a few things to say about this. At the moment, we're a private research center, not for profit, but fairly soon will become a university, a private research university. But we'll have, in addition to a PhD program that we have now, we will also have master's programs. And our focus will, at our center, the center will exist in addition to different departments. So we plan to continue the activities that we're doing now, mostly research, but education will be an important component of the university when it's established. I think there are a few other universities, private universities, that are also interested in this area. One place that I know of is Ahmedabad University. They have a person there who works on quantum algorithms, and he has access to quantum computers in the US. So I think in the future, private universities will be involved in this area. I mean, it's a hot area and with lots of applications, lots of promise. So I can see, private universities getting into this in a much bigger way than they have been in the past, as well as, I mean, private companies, of course, I mean, that. So I think so it's beginning to appear as though the private sector in the form of universities, companies, and so on, will be an integral part of the Indian quantum ecosystem.
Just wanted to add to that. So several of the national institutes already have master's programs in quantum science and technologies of various forms. We have some of these private-public partnership institutes, probably triple ITs are examples of this. So triple IT Hyderabad, for example, has a very active group on quantum algorithms and quantum information theory. In terms of, let's say, faculty positions or job opportunities, I think a lot of private universities in India today are looking to hire in the quantum domain. There is Kriya University, which is not very far from Chennai, which is in near Sriharikota. There is Ashoka, there is Bennett, there is a lot of these institutes I know already have Indraprastha. So a lot of them already have some quantum faculty, and they are looking probably to hire more. Even experimentalists, I know they are willing to give nice startup grants, which will enable them to set up their equipment and so on. So yeah, I think there are opportunities definitely today across the spectrum.
Thank you, Dr. Mandyam, for sharing your thoughts. I think we have time for one more quick question if you want to ask that from the volunteer side, Archon.
Yeah, so that question is specifically for Professor Dash. So regarding the vision of TCG, so you have shared your vision of your center. Also, I'm curious that are you also planning to set up your own nanofabrication facility?
The answer is yes. I think we're in the process of doing it.
Nice.
I mean, we have to. We don't have a choice, actually. Yeah.
Yeah, because for your all the materials and qubit characterization
Yes,
you need.
yes. I think any help, any advice from your side is most welcome.
I mean, I'm not a big expert, but yeah, I've worked a little bit. So I don't see any more questions from the audience. So I will share the final.
Yeah, if you can please share the slide. And in the meanwhile, we'll quickly pull up our final poll question. If the audience can quickly answer that. I think you can share the screen, Archon.
Yeah.
So, you started with a poll in the beginning where you asked people, do they want to go to academia or industry? I think you should add a third one, which is entrepreneurship, because in India right now, there are funds, India-focused funds for young people, $750 million. Okay, VCs sitting with India-focused funds in quantum at that quantum of money. So people who really want to have that bend of mind, this is the time for you to enter this area.
Okay. Okay, thank you all our speakers for that amazing session today. We learned a lot about quantum science, the opportunities in India, and also the collaboration between India and outside in India. And if you're already not a member of SciROI and want to become a member today, please visit our website. And this is our email ID at the bottom if you want to contact with us. And if you have more questions about our session today, you can share or you can write to us about your questions, and we can share that with our speakers. Again, if you can go to the next slide, Archon. So again, just a reminder that we have our upcoming event in September 14 and 15 in US, and I think it's 11 and 12 in Germany. And if you want to register for that, please again visit our website. All the registration infos can be found there. And with that, we conclude our today's webinar. Once again, thank you all our speakers, Dr. Subramaniam, Dr. Das, and Dr. Mandyam. And thanks for, I know it's very late night in India. So thanks again for your time.
Yeah. Thank you, everybody.
Yeah, thank you very much.